Hello, my name is Jesper Gravgaard. I'm going to present to you something about how multi-party computation works, what you can use it for, and how you can utilize it in creating your own solutions on Partisia Blockchain or as a second layer on top of Partisia Blockchain. You will hear about why multi-party computation is the perfect solution for keeping private stuff private and publicizing anything that you need transparency about, and how you can easily create your own solutions where you programmatically decide what is private and what is public. Let me first share some of the topics that I'll be talking about. So I'll tell you a little bit about what Partisia Blockchain actually is, how we got started. Then I'll talk about the secure multi-party computation and how that works. I'll touch upon how zero knowledge computation and CK proofs are related and how they're not related. I'll talk about balancing privacy and transparency, and finally I'll give an example of how you can use the Partisia multi-party computation as a second layer on top of other blockchains. So first, a little bit about the Partisia blockchain. All the way back in the 70s and 80s, Ivan Damgaard actually started working on cryptography here in Aarhus, where I'm also at the moment. And he laid some of the foundational methods that are being used in cryptography. If you look at it, then he kind of both laid at the foundation that is underlying blockchains, but also foundations for multi-party computation, which is a method that can be used to compute on data without actually knowing what the data you're computing on is. So Partisia Blockchain was born out of these cryptographic methods and the environment of cryptographers that work in Aarhus. The purpose of Partisia Blockchain is to provide a solution where you can actually compute on data in private while still getting all the advantages of a blockchain. So we have a bunch of projects already running. For instance, I can point to the International Red Cross that we're helping build some humanitarian token solution for, where you can actually have private tokens inside networks where people are sharing their data, but actually getting something back for the data they're sharing. And we have a bunch of other solutions as well. So what I want to share with you today is, well, what is secure multi-party computation? How does it actually work? And how can you use that in your own applications by creating solutions that use multi-party computation and put that on top of another blockchain solution? So I'll start by giving you some sort of intuition about multi-party computation. The overall idea is actually pretty simple, even though this slide might look a bit complicated. It's actually pretty simple. So the intuition here is that we want to calculate the average salary of 3 people, and you can see these 3 people. They have one has a salary of 4,000 euros, one has a salary of 2,700 euros, and one has a salary of 2,300 euros. And we would like to compute the average, but we would like to do it in a way where none of them actually have to reveal to each other what their salary is. So the method that can be used is, well, if each person actually takes 3 cards and puts a random number on each of the cards, but the sum of the numbers is actually their salary. And then they exchange those cards in such a way that they give 1 card to each of the other 2 people. Then those 2 participants will not know what their salary is, but they will have a number that is a part of the salary. And that means that each of the persons now have 3 cards with a number on it, and if they are willing to add up these numbers and share the sums, then it is actually possible for us to calculate the average, even though none of the people learned the salaries of the other persons. So that's kind of the intuitive idea about how you can actually do computation on data that where you do not have insight into what the data actually is, but you can still arrive at a result that aggregates those data up. What we are doing on Partisia Blockchain and with the MPC solution that we're providing is that instead of people having to share these different cards with each other, well, then we are providing an infrastructure that allows you to get access to servers that will do the computation for you. So by deploying to the Partisia blockchain, you can get some CK nodes allocated. When you want to do some sort of computation, then you can split your data into a number of shares, just like the 3 cards. You can send 1 share to each of the servers that were allocated, and those servers will then perform the computation that was programmed into the smart contract. So that is the intuitive idea about what we are providing. In practice, what actually happens is, of course, that a bunch of math and crypto goes into the solution. So it is not cards that are exchanged, and it is not just taking random numbers that add up to a specific value. The cryptographic math instead allows you to do secret sharing in a way where you can take any type of secret, even of very complicated data, and share them in a secure way where no other participants and none of the participating nodes that are doing the computation will learn anything about the data. The crypto also allows you to perform arbitrary computations and not only do averages. In fact, you can actually program any computation that you want to happen, and then the nodes can perform that computation. And finally, it allows us to actually verify that everyone, both the users and the nodes that are participating in this computation, follow the protocol for actually doing the sharing, doing the computation, and only revealing the result of the computation and not any parts of it. So this entire domain of math has kind of been developed and created for this exact purpose of creating multi-party computation on top of blockchain. So just to dig one step deeper, I'll tell you what happens when you actually put a smart contract on Partisia blockchain that has some CK parts in it. When you deploy the contract on the blockchain, then a number of nodes are allocated to participate in the computation that you want to run. These nodes are actually required to stake a bunch of tokens as collateral to participate in the computation, and that collateral is there to as part of the trust model. So for the nodes to actually participate, they have to stake the collateral. If at any point the node, for instance, decides to stop being part of the computation, then you as the contract owner will be refunded from that collateral. When the contract has been deployed, then you have a CK contract running on the blockchain, and that contract will work in 2 parts. First up, there will be a public smart contract that orchestrates everything about how the computation actually works. So that is receiving the input, deciding when the computation starts, deciding what happens with the result. The actual users that participate in whatever you're computing, they can deliver their secrets as shares directly to the nodes that were allocated. The nodes can perform arbitrary computations on the secret share data, and during that computation they will gain no knowledge about the inputs and no knowledge about any of the intermediate outputs. And when a computation has been completed, the result is actually still a secret, but the contract can choose to reveal the result. And in the average salary example that I presented earlier, the contract would, for instance, work in this way where you deploy the contract, the users input their different salaries, the nodes compute the average, and then the contract choose to reveal what the average is. So to dig even one step further down, then this kind of illustrates what goes on when you put a CK contract on the blockchain. The smart contract has two pieces of code. There's one piece of code that is the orchestration code, which runs on the actual blockchain. It orchestrates everything that goes on, so it can perform any public computation. It can accept or reject any input that is delivered to the contract. It decides when the computation is started, and it is the public part of the contract that decides when outputs are revealed. The other piece of code is the CK computation that is executed by the CK nodes. So when the contract is deployed, as I said, the blockchain will allocate a number of nodes for your computation. Those nodes will then become a CK group, and they will keep track of whatever is happening in this one computation. These CK nodes gather up all the inputs from the users, and when the public contract starts the computation, they then execute the computation that they were programmed to do. And the actual computation that is executed is smart contract code, meaning that it's completely visible on the blockchain. So users that are interacting with a CK smart contract, they can choose to do different things. They can either call a public action on the public contract, they can deliver a secret input, or they can actually fetch their own secrets if an output of the computation was designated to a specific user. So this pretty strong model allows you to create arbitrary kinds of contracts where you do the orchestrations on the blockchain, and you can perform the actual computations on secret data that is kept secret both from all of the users, from anyone who's monitoring the blockchain, but also from the actual nodes that are running the computation as part of this MPC group. I would like to show you what an actual contract looks like, because this entire setup with the blockchain, with the CK nodes, and then with the public and the private smart contract actually allows you to obtain programmable zero-knowledge computation and orchestration. So on the left side here, what I'm showing you is a small part of one of our example contracts. That is a contract that allows you to perform a vote. So you deploy the voting contract to the blockchain, and you have a bunch of users that can then be allowed to deliver votes. Each vote is a secret, and when a deadline occurs, the votes can be counted. So what you see on the left here is actually the program that performs the counting of the votes. And this part of the computation runs on the CK nodes. So the computation is running without anyone actually knowing any of the intermediate results or any of the inputs. So as you can see, the CK compute function here starts by initializing an SBI 32 to 0, and SBI 32 means secret binary integer with 32 bits. So now we have a secret number that we know is 0, so it's not that secret. But what we then do is we iterate over all the secret data that we have received, and for each of those data, we look at whether they are equal to 0, and if they are not equal to 0, we add one more to the number of votes, and at the end we return the number of votes. So if this was executed in open, of course anyone who was following the execution would be able to see exactly which votes were for and which were against. But since this is executed on secret shared data, what actually happens is that each of the nodes do not know whether the vote is for or against. Instead, the crypto ensures that we can still do this computation by actually doing the comparison and adding up the number of votes without knowing whether we are adding 1 or 0 at any given time. And at the end, we have the resulting number of votes, and that piece of data can then be revealed. On the right side, you see part of the orchestration. And the orchestration of the contract here is, what I'm showing here is how do you actually start the counting of the votes. So other parts of this contract will be controlling what happens when you deploy the contract, what happens when someone tries to deliver a vote, and what happens when we are done with the counting. But I've just included the part here where you can actually start the counting. And what you see here is also pretty ordinary code that kind of receives the action that is the start of the counting. Then the smart contract checks whether or not the deadline has been reached or not. If the deadline that has been programmed in has not been reached, then the transaction will fail and the counting will not be started. If the deadline has been reached, then we instruct the CK nodes to start the computation. And we also instruct them that the result that we're expecting is of the type that we want to know how many votes were actually cast for yes. And this part at the bottom is the instruction needed to actually start the computation. Then the nodes will run the computation on the left, and the result will be, the control will be handed back to the orchestration, which can then do something with the result. In our example here, what the orchestration will do is take that result, reveal it, and publish it as part of the public state of the contract. So as you can see here, the code both for the orchestration and the computation is ordinary code, and in this case it is programmed, all of it in Rust. So if you can code Rust that is pretty learnable, then you can create programs that will run on secret shared data with Partisia. All of this is only possible because the blockchain has been built on the architecture where a bunch of the nodes running the blockchain are also willing to run as CK nodes. And the job that they are solving is that they are performing the privacy-preserving computations. They are staking collateral while running a computation towards running it. They are helping produce what is called pre-processed material. That is something that is necessary to actually run. That's part of the cryptography that's necessary to run a CK computation. And then they will run the actual computations. And the payment of these nodes is done in the shape of gas, like any smart contract. But on Partisia blockchain, you have the special situation where the gas is actually not the native currency. It is currencies from other blockchains. So you can bring your own coin from a bunch of other blockchains, and then you can pay for performing your computation on Partisia with the currency of other blockchains. So a few words about MPC or CK computation. Because as you probably saw from what I presented here, then it is not the same as CK proofs. What you get with a CK proof or a CK snark is that one user or person, the prover, can create a proof that can then be published or sent to someone else. And then another person or user is able to verify that that proof is, if that proof is true. So what the proof will allow you to get as input is data from one party or publicly known information. And as output as the verifier, the output you can get is true or false to whether or not the proof is valid or not. So you can verify this one property about something. CK proofs is very useful when you're trying to prove some property, but they are limited to only these yes and no answers for specific properties. While the MPC that we are providing is actually a more general or Turing-complete solution where you can program any type of computation on inputs from many parties, and you can choose as the programmer exactly which results are revealed and which are kept secret. So you can perform very complicated computations, and then you can reveal only the results you choose to reveal. So you can take input from many parties, and you can create any result as long as it is computable with a normal program based on the inputs. So essentially, zero knowledge proof is a subset of zero knowledge computation. This also means that the MPC solution is designed for arbitrary public and private coordination, and not just one of the two. So we kind of have two layers on purpose. We're working with the public part as a solution that can be used for transparency, meaning that you can provide information, transparent information, to anyone that you wish to show transparent information to. This is one of the big strengths of blockchain in general. But we also have this private zero-knowledge computation layer that allows you to keep the information private that you wish to keep private. So you can have a 100% public application that is where everything is public, and the whole state is visible on the blockchain, and all transactions are visible with the information about who sent them and what they sent and what the result was of running the public application. Maybe you want to do 100% private applications where every transaction is private, and where you use the private zero-knowledge computation layer to compute on private data. Maybe you want to create anonymous applications where the transactions are public, but the zero-knowledge computation can be used to keep people or their data anonymous. Or maybe you want to mix and match, where you keep some information private forever. You reveal some information after some time, and you can perform any computation to actually reveal what you wish when you wish to. This is can be very useful if you, for instance, are hit by some sort of regulation where you're required to reveal some information to authorities. It can be useful if you're running time-sensitive processes where you want to keep secrets for a while and then reveal results of computations. And with the solution that Partisia offers, then you, as the programmer who creates the smart contracts, are in control of what is private, what is public, and which computations are performed and which information becomes public when. Finally, some words on how you can use this as a second layer solution. I think this gives an overview where you can kind of see that, on any blockchain, you could run your public smart contracts and do your transactions, and then you could use Partisia just for CK-as-a-Service, meaning that you deploy the private part of the smart contract on Partisia, and you keep the public part of the contract primarily on the other blockchain. And the users that are then interacting with these smart contracts would be interacting with the Layer 1 blockchain for the public parts, and with Partisia for the private parts. But the results of any computations would be mirrored to the other blockchain to make sure that whatever result comes out of the computation is then mirrored onto the blockchain where you need to actually act on the result. So if I put a little more detail to that, you would be deploying a smart contract on the Layer 1 blockchain that actually does whatever public computation, keeps track of the public state, and that has to act on the result of whatever happens in the MPC computation. Whatever requirements you have for the user input validation would be copied to the private smart contract that is then deployed on the Partisia blockchain. The users will be delivering their input on the one hand to the public parts of the input to the public smart contract on Cardano, but the private inputs would be delivered on Partisia directly to the CK nodes that were allocated for that computation. The CK nodes that were allocated, what we do is that we take their public keys and we upload on the Layer 1 blockchain. And this will allow the CK nodes to actually sign off on the result of the computation when they have completed the computation. So the entire MPC computation can run on Partisia Blockchain as a layer 2. The contract receives the input. The computation is executed whenever the requirements are fulfilled. When the computation is complete, the result can be revealed. The MPC nodes can sign the result using their private keys. The signed result can be moved back to the layer 1, where it can then be verified that the result was actually produced by the MPC nodes on the layer 2. This will allow the smart contract on layer 1 to be certain that the result was actually produced by the MPC computation and by the smart contract deployed on Partisia, and will therefore allow the layer 1 to act on the result that came out of the MPC computation. So this was a brief overview of how you would structure a layer 2 solution to actually get MPC computation running on top of your layer 1 solutions today. If you want to see more about how you can actually create these solutions, then you should go to partisiablockchain.com. We have a bunch of documentation there and examples that will allow you to actually see more about how to do this and try it out in practice. And hopefully you will storm there and start creating solutions that use MPC and make your solution stronger.
Wow, thank you, Jesper. That was an amazing show for Partisia, and for me, zero knowledge is definitely a new thing. I'm nowhere technical as you are, and I will try not to embarrass myself, but I do want to ask, and maybe you have brought this up, but what are the underlying technologies, or I would say techniques that are used in the zero knowledge nodes? Like, how do you, what goes behind it? I'm just curious as to.
So underneath this, as I kind of alluded to in the presentation, there is a bunch of math going on. Some of the math is actually pretty well known, and if you're kind of in this MPC space. But for the actual secret sharing, a technique that is called Shamir secret sharing is used for taking any information and then splitting it into shares that are each completely random noise to the node that receives it, but together they actually represent the data that you put in there. So that's kind of one technique for secret sharing. And to the actual computation, an MPC protocol has been specially developed for the Partisia blockchain that is called REAL. And that protocol is what allows us both to perform any computation, but also to verify that all participants are following the protocol. So if at any point there's a suspicion that someone is not following the protocol, it actually gives enough information on the blockchain to unravel every step of the protocol and make sure that to see whether someone was actually following it or not. So it is a specially developed protocol for doing this type of MPC computation.
Okay. Yeah. No. Absolutely. Yeah, I was just curious as to what's behind. So no. Of course.
And that's one of the advantages we have from having the close cooperation with the cryptographers who kind of help us create these solutions.
Awesome.
But I'd say as someone who's actually creating these solutions and deploying them on the blockchain, then you don't need to know all this stuff, because as I showed you, it is actually just a matter of writing pretty simple code that, for instance, adds up numbers or counts stuff or does whatever computation you want to do, and then underneath the hood, our compiler will convert that to the maths that is necessary to actually run on these MPC nodes. So as a programmer, you can use this without having to understand the crypto that goes into it.
Got it. Of course. One thing I wanted to ask you, and before we, if there are any questions from the members, and I'll let you know, but just for my sake, I know you mentioned about the example of the salaries. You were saying, you were showing different sort of ways of not knowing the salaries and somehow coming to an average thing. But in real world, where do you see an implementation or utilization of the real world application of zero knowledge nodes and the applications in Partisia blockchain?
Yeah, I think there are many potential applications for zero knowledge computation, because there's a lot of stuff that you don't want everyone to know. And there are a lot of solutions in the blockchain space that is kind of held back by the fact that everything is public. So I think in any situation where people who are participating in something would prefer their data to not be completely public, then you need some solution to protect that data. And there are solutions for that, of course. There are also existing solutions for that. I think what MPC brings to the table is flexibility in you actually creating smart contracts where you decide, as the person putting this on the blockchain, what do you want to keep secret, what do you want to reveal, and when. So there are a bunch of use cases. I think the average salary that is only a real use case for a very, 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 very limited number of people. But of course, the voting example is a very real example where you want to actually have secret votes, but you want to make sure that the process is followed. Every person only votes once, and we get an accurate count. Auctions are a great example for actually running an auction where the bids are secret, and only after the auction has ended, you will find the winner, and then maybe you will reveal who won the auction and what the price was. You can do much more complicated setups like what I described, where you can have token contracts where the actual balances of each owner, each person who's holding a balance, is actually secret. So when you perform transfers, the transfer is a secret as well. But underneath everything, the balances is of course real numbers, but they are kept secret by the MPC. You could also, a very simple use case is avoiding front running in swaps. So if you can just keep the actual swap that you're doing, which direction it is in and what amount you're trying to swap between two tokens, if you can keep that secret for long enough, just until the swap is actually locked in, then it becomes impossible to front run, even for the nodes executing the swap. So that's a very simple scenario where keeping something secret, even just for a short while, is actually a very great advantage, because it prevents others from acting on that information.
And thank you for that. And I was checking your white paper, and I just came across your whole roadmap. It's absolutely amazing. Just wanted to ask, what phase are you in? Are we in phase 4 right now for your roadmap, or we're for Partisia?
Currently in our roadmap, we have mainnet is live at the moment, and we are so right now you can create and deploy these solutions already. We still have some things in the pipeline where we are kind of making things better and stronger, of course, but everything is live, and the whole development environment and everything you need to deploy these types of solutions is already running. We have all the development tools, we have the documentation, we have the examples, we have a testnet that you can use. So I think currently where we are is that everything is up and running, but we are still adding a lot of great stuff. One of the things we have in the roadmap, for instance, is the bridge to Cardano that will allow you to use the native currency of Cardano as gas on our blockchain. So you can bring Cardano's currency as bring your own coin. And that's one of the things that's still in our roadmap.
Awesome. Cool. No, just wanted to have a few questions. I mean, of course, your white paper is very, very detailed, and I was just looking through it. It's very interesting. So if anybody, I'm sure everyone knows where the white paper is, but if not, then there's the website I can share you. But it's on their website. You guys can check it out. It's just down there. But yeah, absolutely. Thank you, Jesper, for coming in and sharing a bit of ZK zero knowledge information to us, and it was absolutely amazing. And a lot of people obviously in our hackathon are asking, like, if they venture into ZK knowledge, let's say route, what is one from your side? What would be one advice you would give the participants who are going down that route?
For me personally, at least, I think the first step was kind of accepting that it actually works and seeing for yourself that it works. So I think a really good way to get started is actually by trying out some of the examples that are prepackaged, to actually try them out on the test net, try to play with them and see how it works, to get a feel for it. And then I think if you want to dig in, it is a very deep hole. You can dig as deep as you want, but there is a lot you can do without having to understand the maths. So I would definitely start with the examples, and then try to modify them and try to see if you can make them do what you want to get them to do.
Thank you for that advice. So there you go, guys, straight from Jesper himself. Hopefully a lot of people, we should be seeing a lot of people going into zero knowledge. It's one of the big routes that a lot of people have chosen. So let's see what we get for the end of the hackathon. But if there's any questions for Partisia Blockchain, please, if you haven't had the chance to view it right now and ask, go to our Discord, just ask away, and we will make sure that the questions are reverted to Jesper and Roderis. So definitely on that. So thank you again, and thank you for coming in, and we'll catch up soon. Thank you, guys. Thank you for
being. Thank you for letting me be here.
Thank you. Our pleasure. Thank you. Take care.
You too.